Hi, how's it going? My name is Erway, I'm from AppNeta, and I'm here to present a shortened version of a meetup talk I gave a few months ago called Python, Go, and the Cost of Concurrency in the Cloud. So the point of this talk is to sort of talk about the differences between scripting languages like Python, Node.js, and Ruby, and how going from one of those languages to Go for a very specific service over at AppNeta was something that not only yielded cost benefits, but also, not only performance benefits, but also yielded cost benefits for our AWS usage. And who am I? Well, I'm the chief architect at AppNeta. I'm a Python, C++, C systems hacker. I only have a little bit of experience in Go, but my preliminary experience has been pretty great, and I just wanted to share it with you. So the things I like about Python is that it's fun to program. Like all the scripting languages, a little bit of code goes a long way, and you can use built-in maps and sets and arrays and tuples that are a lot more fun than in other languages. The things I don't like about Python is that it's slow. You know, it's not too fast, but it's not too slow. And if you want to do anything concurrently, the big problem is that you'll run into the dreaded global interpreter lock. And that's something that's common with Ruby and Python and Node.js, all three, which is that when you're running program code in any of those languages, the interpreter can't run in parallel. So anything you do has got to be serialized through the global interpreter lock. And that's fundamentally different in Go, which is a new language from a bunch of smart guys that goes after statically typed, fast performance, but with the fun-to-use programming paradigm that you might get from Python. And so what's the similarities? Well, they both have built-in types like maps, arrays, and strings. You know, when you find yourself optimizing your code in one of the scripting languages, you might call into a lot of C modules. You can still do that in Go. And like Python, you don't have to implement classes or methods based on object-oriented inheritance, but you just implement like duck type sort of classes, and there's this dynamic feel. You don't pepper your code everywhere with type declarations. You just use automatic type inference, and so you don't actually end up doing a lot of the grunge work of having to worry about types as much as you might think. The differences between Go and Python are that Go's a lot faster. You know, it compiles the native machine code. The memory usage is much lower. Everything you do in Python is going to end up probably invoking a dictionary lookup in a hash table because everything's got a per object dictionary for the methods or attributes for each of your class instances. And Go was built from the ground up with concurrency primitives in mind that I'm going to talk about, Goroutines and Channels specifically. Also, Go has curly braces, which is kind of a bummer, but what can you do? And among all the other languages that I put on this slide, you can see that Go's got pretty easy to use concurrency and a lot of the benefits of Go using a compiled language like C++ or Java. But the key differentiator is that there's this easy to use concurrency. And the previous version of this talk was sort of a talk about Go and how you could learn it for a Python audience, but I don't want to get too much into that. There's lots of information online that you can use to understand how to learn Go. But basically, Go provides these two primitives called Goroutines and Channels. Goroutines are lightweight threads, and so you can have tens of thousands or hundreds of thousands of goroutines. And then there's channels, which is the way to synchronize between your threads or to communicate between your threads. Whereas if you try to put an element on a channel, you'll be blocked until a consumer tries to read from that channel. And so they're very useful for systems where you might have written a Python function. You might be familiar with generators, and the generator is like in the upper left-hand corner, this function that yields values iteratively, and then the caller in the bottom left-hand corner is basically consuming values and controlling the flow of the producer function by consuming values, which and then the producer is blocked until the next value is consumed. So you can do the same thing with Go, except you have to interpose the consumer and the producer with a channel. And in this case, the channel is unbuffered, so when the fib routine tries to put a value after invoking a goroutine with the go space func there, it's invoking an anonymous function that tries to put values iteratively onto a channel. And then just like in the previous Python example, the main method is consuming values until the channel's closed. But the key thing with the channel here is that you can have any number of goroutines producing and consuming values, and none of them have to really worry about synchronizing access via mutexes or locks. They just need to produce values and consume them, and then you can use as many cores as you want to put data into and out of that channel. And so this is a cute slide from Brad Fitzgerald's talk last year at GoCon, where he thinks that Go and maybe Erlang are the two most beautiful ways to use concurrency, but when it actually comes down to efficiency, Go, he believes, is the top in the Magic Quadrant of this particular arena. And there's a lot of cute Magic Quadrants he has for the programming languages if you go look up this talk. So who cares? I'd argue you care, because concurrency is one of the most important things in the modern computing environment. You know, if you're writing code for the cloud, or if you've refactored your whole code base to be using microservices or a service-oriented architecture, this is fundamentally different from the assumptions 10 years ago when you would write a LAMP app or a Rails app and you'd just have a 3-tiered web stack. It's because the assumptions on latency between all your components really fundamentally change, and so that's when the concurrency of your language is really going to start to cost you time and money if you're not careful. These days, everything that you used to do with a long-living persistent socket, now you're probably doing with a whole bunch of HTTP round trips, right? So whereas before your database was just a pool of long-lasting sockets to MySQL, or if your queue was a RabbitMQ server and you could just put thousands of requests per second over a single socket, that's no longer the case. You now have SQS, for example, where you're going to have to make thousands of requests. To get that type of throughput, you're going to need to have hundreds of sockets open concurrently, because every HTTP round trip has a built-in latency of a few milliseconds at least, and probably 10 or 20 milliseconds depending on how fast the service is on the other end. But you know, in this day and age when we have unlimited scale to S3 or SQS, all of those calls can certainly handle the throughput that we used to have, but their language is just going to be a lot more limited if you can't effectively use concurrent sockets to make the same throughput guarantees real in this modern world. And that's really what I'm trying to get at. And maybe you're saying, okay, I write async code in Python or Node. I have all these callbacks in my Node.js. I wrote a Ruby event machine program. I use a lot of Tornado or G-event code. And it looks async to me, and I think I'm using multiple cores, but you're not. You're still stuck with the single-threaded interpreter. You can schedule asynchronous network I/O, you can schedule asynchronous disk I/O, and you can switch between the callbacks for them, but at the end of the day, your interpreter is only going to be able to run one bit of code, one line of code at a time. And that's a problem, because these days you're not just waiting on a whole bunch of binary data shoved over a socket. You're doing an SQS put with your base64 encoding some JSON data, and then you have to sign it, and then you have to do a TLS handshake just to get to talk to your API. And there's a lot of compute-heavy stuff going on that's going to have to be serialized because you're using a single-threaded interpreter in Node or Python or Ruby. And that wasn't true a long time ago when we had long-lasting sockets. So it's not as simple as just having pure disk I/O that you're sitting around waiting for. And that's really the the other trend that's sort of leading to the need to use more concurrency is that we got all these cores now. And how are you going to use all your cores if you have a single-threaded interpreter, right? I would say that this is kind of a strong opinion, that people who are using Docker are sometimes using it as a crutch to get around the fact that they have an app that's written in Node or Ruby or Python that's stuck using pretty much just one core, and then to scale up, they need to just have a whole bunch of containers so that their programs don't run into each other RAM-wise, right? And so that they can bound the resource usage of any single server and then just scale it out by having dozens of containers on a single server, and then that's how you use all your cores. And that's not always the optimal way to write your system. That's kind of a strong opinion, though. And so the motivating example for this talk is about a program that we were running that does some analysis maybe a few hundred times a second. It was slowly ramping up to be 1,000 times a second. We were running this analysis task, and then we had to put a little bit of data into S3, 70 KB in this example, 1,000 times per second. And that was kind of getting expensive. Why is that? Well, that's because the S3 put cost is about $5 per million. So that's kind of expensive for all those puts, especially 1,000 times per second. Whereas SQS puts are 50 cents per million, and then Kinesis puts are even cheaper, 1.5 cents per million, but you have to provision the throughput, et cetera, et cetera. So what we got the idea was, well, if we're going to be doing all these puts to S3, why don't we try to do fewer puts and save on the cost by interposing SQS in between my writing to S3 and then writing a batch writer program that read from SQS and then batched up the files that we were going to put to S3 into larger batches so that we can save on the put cost. And so we were starting out with a problem that was going to cost us about 13,000 bucks to do 1,000 writes per second to S3 per month, and that seems a little bit expensive. So just right away, if you could interpose SQS into the picture and write this batch writer program that's consuming from SQS the data that was going to go to S3 and then batching them into files where 10 blobs per batch was going into S3, you can right away cut 75% of your cost off this program by cutting the put cost by 10x. Of course, you have to pay a little bit to get things in and out of SQS, which has a maximum batch size of 10. But it definitely seems worth it to write this program just from the economics of having batches of 10. And then if you want to go to 100x
reducing your S3 put cost, then you're getting these larger files, and then you're starting to deal with a program that really needs to manage concurrency a lot more effectively if it's going to be able to achieve 84% cost reduction, as in this case. And so and then if you want to try to do 1000x at a time batches, it's actually diminishing returns because you're only yielding another 1% for that 10x increase. So what we did was I wrote about 140 lines of Python to implement this algorithm to try and test out this program. And it was pretty easy to do. I received messages from SQS 10 at a time. And then after a certain timer would flush, because I wanted to make sure I was ensuring aliveness on this data, I would go and try to write the data to S3. And right away, I ran into some implementation difficulties. That is, the reading of the data from SQS took about 20 milliseconds per round trip. But then after I was flushing a buffer out to S3, that would take as many as a few hundred milliseconds to write it out to S3 and then do the dynamo writes and also the SQS deletes. And so it was very difficult to scale this because it was in a single-threaded Python interpreter. So to try and be able to receive and write all the 1,000 messages per second that I wanted to get out of SQS, what you end up doing is just adding more processes to your system, right? So we had 40 or 50 or 60 processes, all consuming from SQS and then trying to put into S3 like crazy. So I could never really get the gains I've shown you, the 84% cost savings using Python, because right away none of them are sharing the same buffer, right? I was never able to actually get 100 messages per buffer when I flushed to S3, and that's because I was over-provisioning pollers to make up for the fact that the write side of this program was slower, a lot slower than the read side of this program. So there was no real way to scale the independent polling and the writing separately. And also, these programs don't share memory, right? They're all just different processes in Unix, and so there was no real way without doing a lot of IPC craziness that Python's not that good at to get at the fundamental problem, which is that I don't have any concurrency in my Python interpreter. When I wrote the Go program, it was a little longer than 140 lines, but it was very simple from the high-level view, where I had a Go channel and another channel in and out of this batcher program, where all my messages, as I was polling from SQS, and I could independently scale the number of readers, were going into this Go routine that would just batch things pretty much exactly at the size I want, 100 at a time, and then I would send them to a pool of Go routines dedicated to putting the data into S3 and writing it out to Dynamo. And so that was, this finally gave me the 84% savings that I was trying to get out of the modified program. And so the moral of that taught me that, concurrency costs you money. If you don't have a language where you can just very effectively use concurrency and try out new ways of using concurrency, you might be making a lot of bad decisions that are going to cause usage-based pricing APIs to be really ineffective in a lot of cases, leading to RPCs when you don't need to, just to get over the fact that your programs are all stuck in single-threaded processes, and then a lot of over-provisioning, over-polling, where you don't need to be doing. And maybe you're asking yourself, okay, I just write Scala code and it's beautiful and I don't have to worry about this. And that might be true, but I would argue that there's no language like Go that has a three letters that you have to type in just to get a new thread launch, G-O and space. And I'd say that the ease of use of doing that, G-O space and then the function name, and then using channels and not having to worry about mutexes or locks, I think it's one of the easiest ways to effectively use concurrency and not have to think too much about launching a thread with a run method and having to make a new object and all that stuff. And additionally, you aren't going to be launching as many threads in Java or C++ as you could, because you simply will run out of stack sizes and your program will run out of RAM. Whereas Erlang and Go can both go up to millions of threads per program because they have very lightweight threads and a very small stack size. So I'd argue that there's real benefits to using a language that supports concurrency, especially when you're moving to one of these cloud-based architectures. And now you're probably saying, well, I don't do 1,000 things per second with all these APIs. Does this really apply to me? And I'd say you really should think to yourself, I'm turning all my programs into microservices right now. Maybe you're starting to use a lot more cloud APIs. Are you making calls in a controller or a task where you're calling 3 independent services sequentially, like service A, service B, service C, and none of those calls actually have to interact with each other? If you're doing so, you should really be doing that concurrently. There's no reason you should be waiting for A to finish before you make the call to B and then the call to C. That's a limitation of your language. That's a limitation of your thinking that you just can't use enough threads, or it's just too convenient to use threads that you're not doing so. And so that's sort of the message I want to give to you, is just think about, what are you waiting for? Maybe you should be waiting less. That's it, and thank you. I hope this was interesting. We're giving away a BB-8 Droid, and a lot of the performance benefits of the program that I'm talking about were measured using a performance monitoring product that we sell over at AppNeta. Thanks very much.